Alrighty, so page 2 of our notes for this particular unit has to deal with measuring position, and we're going to measure it in the form of a z-score. So that is already highlighted there for us, underlined for us. And so in the process, we're going to have to be able to work with that z-score and understand what a z-score is. So first of all, we'll talk about our formula. And anytime we see a star, I don't remember if we talked about this yet, a star is pretty much you're guaranteed to see it on the AP exam. So in words, so what we're going to do is we're trying to figure out how far a piece of data falls from the mean, okay? And we're going to do that in the form of standard deviations. Okay, and I think here is where I've probably gone back to page 1 and I filled out this little normal curve. So here's our standard normal curve. Okay, in the middle is going to be my mean. Okay, my mean falls in the middle, and so that means that my middle is going to be 0 standard deviations from the mean. This is going to be +1 standard deviations. This is going to be +2 standard deviations. And out here, there's a mark that I can't see, but it's going to be +3 standard deviations. Likewise, when we go to the left, this is a -1, this is a -2, and this is a -3. So we're talking about standard deviations above or below the mean. Okay, so if I find something that is 2.8 standard deviations below the mean, I know that it's a really rare piece of data because it's way out there. And we'll talk about percentages when we get there. I mean, that's why we started out talking about percentiles, because our normal curve allows us to find percentages. But that's what we're doing. So we are finding the standard deviations from the mean in observation and falls and in what direction. Okay, so what that means is on the AP exam, if we're asked to describe... Nope, we're going to back that up. I'm not going to describe it. If I'm asked to interpret a z-score, when we interpret a z-score, that's what we're asked. We need a distance and a direction, okay? That's the two things that we have to have in that, okay? Okay, how far and in what direction. So now we have to have a formula for this z-score. So when we talk about this in words, it's going to be the observed value minus the expected value divided by however big my standard deviation is. Okay, I don't like that. I won't abbreviate that. Let's go with standard deviation. We can write that out. Having trouble with my S's. That's written out in words. So now we need a formula for this. Okay, and here's where, again, we need to understand when we talk about samples and when we talk about populations. Okay, first of all, an observed value. An observed value is just going to be some value of x. My expected value, well, the expected value is going to be the mean. So if I'm dealing with a sample, it's going to be x bar. And the standard deviation is going to be Sx. There we go. Okay? However, if for some reason we were talking about a population, my observation is still going to be an observed value x. However, my mean is now going to be mean mu, and my standard deviation is going to be sigma. Okay? So do note there's a difference between there. And I'm going to wish I had my formula sheet, but I don't. So right now, I don't have a copy of my formula sheet ready to go. I'm not want to kill time finding it, but I'll introduce that later on, and we'll get there. Okay, so that's how we're going to do that. So now this allows me to do something. So if I wanted to compare an ACT score versus an SAT score, doing this, finding out how many standard deviations above or below a mean something is, allows me to do that. Okay, now we're going to call this a standardized score. So because if we read this, Peyton Manning scored 24 points in his last game. The NFL mean for points is 17, and the standard deviation is 4.5. What is Manning's standardized score? So a standardized score is in terms of standard deviations. So again, if I wanted to write this out, and actually this particular problem is missing something that it's an assumption that we'll have to make down the road. I don't see that here, but we're just going to deal with it. That's a horrible curve. Let's try again. Okay. Peyton Manning, we have a mean of, we know that the mean is 17, so the typical in a scoring in an NFL game, the average is 17 with a standard deviation of 4.5. So I know that this is going to be 21.5 at one standard deviation. I'm going to add 4.5 again, and I'm going to get 25.26. So I'm drawing out the standard deviations above or below the mean. Now I know that Peyton Manning scored 24 points. 24 points falls right there. Okay, so but what we want is we want a specific value. So we're going to take, again, we're going to find a z-score for this. Again, right up here, it's observed minus expected divided by our standard deviation. Technically, I'm dealing with the population on this one, but we'll go with, it doesn't matter which one we go with. Again, if we go with the words, it's, again, irrelevant. What did we observe? We observed Peyton Manning scoring 24 points. How many points did we expect Peyton Manning to score? Well, that would be the mean in 17. What's the standard deviation of points scored? Well, we know that. That's going to be 4.5. So if we divide that out, that is 1.56. And we can see that here, that's a horrible looking 21. But here was the value we were talking about. We were trying to find where did 24 fall? Well, 24 fell right about there. And that is, again, you can't see my pen, 1.56 standard deviations above the mean. Okay, so that's what we're going to write. Peyton Manning scored 1.56 standard deviations above the mean. So when the AP grader is looking for 1.56 standard deviations and above, we have to have that direction in there. Okay, so we have to have a distance and a direction. Okay, that was just with one. So now we're talking about the whole purpose of this is actually to develop it amongst and compare two different things and figure out which of those two different things is better because they're on two different scales. Okay, so let's look at example 4. NFL players are given agility and strength tests as part of their training. Suppose that Tom Brady earned a score of 86 on his agility, where the national average is 80 and a standard deviation of 6.07. Von Miller earned a score of 82 on his strength test. The strength scores have a mean of 76 and a standard deviation of 4. Who performed better on their test relative to the rest of the NFL? Now, one strategy here is once we get used to doing curves, we could just draw out a curve. Okay, so Tom Brady, this is the agility curve. Okay, I'm sitting down on the couch and I actually don't write very well. Maybe I need to go to somewhere else. Anyway, here is my agility curve. We know the typical athlete. Okay, if we come out here, the national average is 80 and the standard deviation is 6.07. Okay, so here is the middle of 80. I know that one standard deviation above is going to be 80, therefore 86.07. I know that Tom Brady scored an 86. So that means that Tom Brady is going to be right there. Now we can do the same thing for Von Miller and the strength test. We know that the mean is 76 with a standard deviation of 4. Oh my God. Again, we know that the strength is the average NFL player is 76, has a standard deviation of 4, so that means that one standard deviation is going to give me an 80. The next standard deviation is going to give me an 86. How about 84? Okay, Von Miller scored an 82. So there's Von Miller's 82. So based upon the pictures that we drew, who is better? Well, Von Miller is going to be better because he was more standard deviations above the mean. He was this far versus this far. So we drew it out with a picture. That would be an acceptable solution for this. However, I'm going to want us to be able to do the numerical solution out of this as well. So that means that we have to come back here and we're going to figure out a z-score for Brady. And then we're going to convert his agility test into a standardized score. So we observed Tom Brady with an 86 on his test. We expected Tom Brady to get the national average, which is 80. And we're going to convert that into standard deviations by dividing by 6.07. So that means his z-score was 0.99, which we knew already because we saw that come in right here, just underneath 1. Okay? We're going to come over here and do Von Miller's. For the strength test, we're going to convert that into standard deviations. Again, now once I can, so we observed him with an 82. We expected him to score a 76, and there's a standard deviation of 4, and that turned out to be 1.5. Okay, so now we have both Brady and Miller, we have their scores on their test converted into standardized scores, which is going to be z-scores, and from this, we can say Miller was better because his z-score of 1.5 was further from the middle. Okay. Now, sometimes we have to be careful as far as we're looking at distances. Here, we're looking at something, a positive means that we are better than the rest, okay? But sometimes that could be negative. So if I'm looking at race times, typically, so the further left you are on race times, the better you did. So we have to pay special attention to that. When we get to those. All right. So that took care of this particular lesson. All we did was take care of